Okay, let's start doing some of these puzzles in plane geometry. So our puzzle book here, and have a look at what we're going to be working with. That we'll be doing. Page 44. These are the main, or maybe most useful, theorems that are given to us. We will refer back to here. And we will begin, say, right at the top of this page. All right. Calculate the measurements of all angles in the given tetragons. Okay, so this is, let's make clear, this is page 44. Write that one more time. And we're starting with 10. Top of that page, number 10, and I'm just going to do a quick sketch here. I'm not going to make anything congruent, won't even be similar, right? Similar is same shape, but different size. Congruent is same shape. So they have something like this, and they say this is alpha, this is 4 alpha, this is 2 alpha, and this is 3 alpha. Now, let's talk about Euclid's fifth, because Euclid's fifth, you have a line and a point that's not on that line. How many lines go through this point that do not intersect with this line? And we would say just exactly one. One and only one. One line. That is Euclid's fifth. Euclid's fifth axiom, sometimes called the parallel postulate. And it is the reason why triangles are 180 degrees. And his name is the reason why we have this adjective for geometry, Euclidean geometry. This guy is like the original gamer for this stuff. So 180 for, whoa, look at that. I wrote that. And a tetragon, didn't I? Draw a diagonal on a tetragon, and you got 2 trigons. 180 plus 180, well, that's 360. Thank you, Euclid's fifth. And the theorems that result from it, like this 180 degrees, that's how we get these tetragons to 360. So here we have a tetragon, 4 sides is a tetragon. And we know if you add up all the interior angles, all these ones on the inside of this shape, this tetragon, we get 360. So we don't know the numbers of that. Remember, we're using 360 thanks to the Babylonians. They're some of their favorite numbers. 60 was like their favorite number. Well, that's why we have 360 and 180. Just Babylonian tradition. It's the only reason why. Nothing special about those numbers. So, tetragon adds up to 360. And that means this alpha plus, 4 alpha plus 3 alpha plus 2 alpha. Add up to 360. 5, 8, 10, 10 alpha equals 360. 360 degrees. So alpha is how many degrees? We multiply each side by the inverse of 10. the multiplicative inverse of 10. And when we do that, alpha 36 degrees. That was 10. That was 10A. Should we do 10B on the same piece of paper? So let's see. Let me sketch this figure here. I think we got enough space. Got another quadrilateral, right? Because in number 10, they're asking us find the measurements, the angles, in this tetragon. And this is not congruent. It's not even similar. I don't know if the proportions are right, but they call that angle beta. This is 150 degrees. This is beta. And this is beta. So because we can take a tetragon, oops, a very good tetragon, and we can turn it into two trigons, 180 plus 180, that's 360. We know this tetragon has angles that add up to 360. So 1, 2, 3 beta angles in degrees. So 3 beta plus this 150. Oh, I ran out of space here. Equal 360. All right, let's do this properly here. Okay, so 3 beta plus 150 equals 360. And there really should be little degrees here, but kind of lazy, so I'm not going to write those at the beginning. I'll write the degree symbol at the end. So we add the inverse, add the additive inverse of 150 to each side, or add the opposite of 150 to each side. So adding the opposite of this will make it 0. 3 beta plus 0 is just 3 beta. Then over here, I had to do the same thing to this side. There I'm adding the opposite of 150, which is negative 150. So 3 beta is what? 360 plus negative 150. Is that 210? So from here, I have 3 beta. I want just beta. So to do that, because beta is attached to something with multiplication, I need to use a multiplicative inverse. Because if I do that, I get the multiplicative identity, which is just 1. 1 times beta is just beta, and I can write that. So I use the multiplicative inverse here on each side. Beta is 70 degrees. Now, here we have the answer. Here, maybe we didn't complete that. We need to say which each, so alpha here is 36 degrees. That's 36 degrees. This one is 72 degrees. And you have to do the same thing for these angles to get it right on the exam, to solve the puzzle. And as the theorem goes, it's basically this, we're given this, prove that these angles, or find, so as written as a theorem, this would be like if, or suppose we have a tetragon. If we have this object, then these angles will be 70 degrees. Okay, so that's 10A and 10B. All right, 10C here. 10C. This is page 44. And let's see. We have this here. I give something like this. 100 degrees, so it's a little more than 90. Like that, maybe. And then it does give us a 90. Like this. And then down here for, I don't know what that angle is. Again, if we were to look at the book here, we're on page 44. I'm just copying this sketch. And where this puts an angle and a dot, my tradition is just put a little square thing. That means 90 degrees. That means 90. So, and we're given this tetragon. And we're given some information, like this is 100 degrees, and this means 90, that little symbol there. And just don't write it out, because you can just do it like that. Little corner box, and then 78 over here. 780, that's a really big degree sign. Make your degrees symbols small. Okay. So, what do we know? What do we know? We're given this, and we're supposed to find, given this, prove that these angles are going to be what they are. Find these angles. So our theorem is basically, if or let this tetragon exist with these parts, and it will be the case that, or you could say then, if then these angles will be the measurements that we're about to find out. So here's how we find this out. The quickest way is to go, well, look at this. This is a linear pair. Because one thing that's with these figures, what's given is kind of an implication. It's implied with the figure. They don't want to write a lot of words. We're looking at this, we're assuming this is the quadrilateral or the tetragon that they're talking about. This is one line. These vertices here are on the same line. So sometimes in the figures, there's some, maybe not assumptions, but there's some unspoken givens. Here we have a linear pair. So that means 180. 180 going this way between just two angles, this one and this one. So that means this is 102. Has to be. Has to be. That is true. And over here we know this has to be 80. Because this is a linear pair. This angle here, this exterior angle to the tetragon, this angle is given to us as 100. You can see this is a linear pair. These are adjacent angles. They're supplementary. They're supplementary because they're a linear pair. They're supplementary because they add up to 180 degrees. So, and we know tetragon adds up to 360. We have 3 of these angles, so subtract the sum of these from 360 and you get the measurement for this one. And I know I said I'd be doing most of these. I'd be doing most of these. I'm going to have you do that arithmetic. Okay, so that was 10, A, B, and C. Let's see, I'll have to get this back as a bookmark. And now we'll be doing 11. Okay, so piece of paper. Okay, you go 11. Okay, given angle alpha in segments A and B, construct a triangle ABC in which AB is equal to A, AC is equal to B. Okay, we are on to 11. And 11 is, well, it starts with something that's mostly just says, sketch this. 11A. So, like, this is given angle alpha, and then 2 segments, line segments, A and B. So given those 2 things, construct a triangle named ABC. Construct a triangle named ABC such that in your drawing, it wants us to label it like this. The measurement of segment AB is the same as A. Measurement of AC, same as B. And what else? So once angle BAC, the measurement of that, I want that to be equal to alpha. Okay, so we don't know what the degrees are or what they want. I think it's just labeling. So we're going to have a triangle, a tetragon, or I'm sorry, a trigon, 3 sides, 3 angles, a trigon. Trigon ABC. We'll say here's A, here's C, here's B. Well, let's put So we're making trigon ABC. And I believe it just wants ABC. And we'll make what there's segment AB. And it wants the measurement of AB to be equal to A. So we'll just label that A. We don't know what it is. It wants AC, the measurement of this segment, AC, to be equal to B. So we'll just label that B. And it wants the measurement of angle BAC, BAC. So B from here to here to here, this angle here. It wants that angle to be equal to alpha, or to be the name alpha, is alpha. I suppose if we're using the symbols from the puzzle book. So this would be alpha. And then for it to be a trigon, it needs 3 sides. So there's our angle. These 2 segments, A and B, whatever these measurements are. And the angle made by these line segments at vertex A is alpha. And to make this a trigon, you just put in our 3rd side right there. This is 11A. 11A. All right, so now we're moving to 11B. And we have the other side of the paper for that. So 11B, given angles A, or given angle alpha and beta, angles alpha and beta, and segment A, construct a trigon ABC in which AB is equal to A, CAB. Let's see, can we, it's going to be something like this. Can we use what they did here? So they're giving us alpha and beta. So maybe we can use this drawing for B. Let's see. So we're given alpha and beta and a segment A, and it wants ABC, in which AB is equal to A. So we have that in this trigon. And it wants angle CAB, angle CAB to be alpha, and it wants angle ABC to be beta. So to do 11B, 11, let me just name this beta. We'd be sketching the same thing, ABC, this angle, this beta. So this sketch, this figure, satisfies what they wanted in 11. Basically some instructions to draw something, not really writing a theorem. There we go. Okay, let me flip to the other side, and we'll do 12 here. Well, 12, okay, this is number 12. I won't actually do 12. I'll just do some things in the spirit of 12. So here we got a line. And let's see, how do we make a perpendicular somewhere? Let's start with this. Let's put a point on this line. We'll put a perpendicular through there. First, mark that distance. Over here. And we know that this goes, it's on a perpendicular through there. And we know that if we call this A, if we call this over here Q, we know that this is the midpoint. And let's see here. If we go from here to here, if these two segments are the same length, then you know that this trigon made here, this is where we have a 45-degree angle. If we wanted to make, let's see, if we wanted to make a 60-degree angle, we just need an equilateral triangle. So we'll go from here. Since we already have this perpendicular here, makes it quite nice. Oh, and should continue this line. Let's see, since we use this as the center, we know these are equidistant here to here, this point to this point. All right, it's true that these are the same distance, and we checked it. This is the same distance, so here we have, that's the same length. $60 degrees. So 12 and 13, not going to do those. Those are just some constructions. Go straight to 14. So 14a. What are the measurements of adjacent angles, alpha and beta, if angle alpha is 50 degrees greater than angle beta? So we're given adjacent angles, alpha and beta, and it says that angle alpha is 50 degrees, the measurement of alpha, like that, we could write, is 50 degrees greater than beta. Now we have to assume something here. There's something else given, because there has to be on number 14, because this and that, these are this angle here. If this could be alpha, this is beta, maybe not with this property necessarily, but these are adjacent angles. So I think what's given here, or maybe something that's lost in translation of this Polish book for me, is that these adjacent angles, alpha and beta, they form a linear pair. They are a linear pair. So there's a line, and then there's one line coming off that, and that's where alpha and beta come from. Adjacent angles from a straight angle. So one ray going through here, this. So here's our angles. One's alpha, one's beta. So they're a linear pair. They're supplementary. And in 14a, it says what we have. We have beta, and we have, this is beta plus 50. So we add these because these adjacent angles, they're a linear pair, they're supplementary. They add to 180. So we have beta plus 50 degrees. This angle here plus this angle here, beta, that equals 180. Take the parentheses off. We have 2 beta plus 50 equals 180. Let's add negative 50 to both sides because that's the opposite of what we have here. Plus negative 50. There we have 2 beta equals 130 degrees. So beta equals 65. So one angle is 65 degrees. That's beta. And alpha is 50 plus that. So alpha, this angle here, is 115 degrees. That's 14A. 14A. Something similar, I think, in B. Do 14B. Okay, again, they're talking about adjacent angles, and we have to assume that these are a linear pair. Just have to assume that. Otherwise, there's nothing to add up. Or we don't know what the total would be. And I just drew that. I don't even know why I did. This is a linear pair of adjacent angles. They form this straight angle here, but this might not even be close to an accurate. What does 14b say? One of the adjacent angles is 7 times greater than the other. What are the measures of these angles? So let's see, we have an alpha, we have a beta, and let's say beta is the bigger one. Beta equals 7 alpha. And we know that these angles added together, we'll use the alpha form of beta, because if we write beta in here, it won't help us very much. We only have one equation. We'd have 2 unknowns. Here we have one unknown symbol in one equation. So we can solve this. 8 alpha equals 180. So multiply each side by 1/8. 180 times 1/8. This leaves us over here with alpha. And what we have 8 to 180. 16, 2, right? We put 2 again. 22.5 degrees. Alpha is 22.5 degrees. 22.5 degrees. So that makes beta, this other angle, the other adjacent angle, to solve this puzzle, to win this game, to write this theorem. If we have a straight angle, if we have a linear pair, or let alpha and beta be a linear pair of angles, such that beta is 7 times greater than alpha. Let that be the case. Then alpha would be 22.5 degrees. Proven. That's our theorem. So you'll have to do the arithmetic on this, get the answer. I'll let you multiply. But I think it would be what? I'll do it. 7 times 20, that's 140. Let's see, 2.5 times 7. It says 14 plus 3.5 is 17.5 plus the 140, 157.5. You can check my arithmetic on that. So what was that? That was 14. That was 14B, I think. 14C. So again, we're talking about adjacent angles that are in a linear pair. So got a line already coming off that. Something like that. And there's a ratio with respect to what they say, alpha. Does it say 14? No, it doesn't give any symbols. Forget I said that. It says the ratio of the measures of adjacent angles is 2 to 7. What measures are these? So 2 to 7. So 2x, 7x, and since we're talking about a linear pair, these are supplementary angles. So 2x plus 7x equals 180 degrees. 9x equals 180. X equals 20. So multiplied both sides by the reciprocal. So turns this into 1 times x, which is just x. I get 20 there. So this angle here, 40 degrees. This angle, 140 degrees. And that checks out because it's a linear pair. They're supplementary. They should add to 180, and they do. That is 14C. We're doing 15. Okay, here we are, 15A. It says angles alpha and beta are vertical angles. Angle beta has a measure, angle beta here, has a measure that is 15 degrees greater than half the measure of alpha. So here we have beta equal to 1/2 alpha plus 15. What else do we know? Well, we're given alpha and beta are vertical angles. That means beta, well, if they're vertical angles, that means they're formed from 2 lines. Vertical angles are like that. Those are vertical angles. Alpha and we have beta. Thing is, with vertical angles, they're equal. Beta equals alpha. Beta is also this, so we can say 1/2 alpha plus 15 is equal to alpha. Alpha minus 1/2 alpha equals 15. 1/2 of alpha is 15. So alpha must be 30. 30 degrees. That's the answer to 15A. Right? It tells us we have vertical angles, alpha and beta. It tells us beta is 15 degrees greater, 15 degrees bigger than half the measurement of alpha. So here's beta expressed in terms of alpha. We know beta is equal to alpha because it's given that they're vertical angles. So they're equal to each other. So we set that up right here. Set that equation up, and then we solve for alpha. That's 15A. 15B. And this is page 44. 44. Page 44, 15B. So one out of a pair of vertical angles is 75 degrees greater than a certain angle alpha. And the other vertical angle is 4 times greater than alpha. So they're talking about a pair of vertical angles. So these angles are equal to each other. They have the same measurement, or the measurement is equal. I should say these angles are congruent. Those are vertical angles. And they talk about one of them in terms of alpha. They say it's 75 degrees greater than alpha. And they talk, the book gives us the, talks about this other angle, which is a vertical angle to this, in terms of alpha as well. It says it's 4 alpha. 4 times alpha. These are vertical angles. So it means we have a situation like this. Oops. Sorry about that. So let's call this theta. This would be measurement theta as well, because they're vertical angles. And it talks about each of these in terms of alpha. It says this is alpha plus 75. Maybe this one is 4 times the measurement of alpha. But we know these are vertical angles, so they're congruent. They're the same angle measurement. They have that sameness. So let's add the opposite of alpha to both sides. We get 75 equals 4 alpha minus alpha. 75 is equal to 3 alpha. Alpha is equal to 25. And this is what is the measurement of the angle. Right? So this is alpha. This is the end of our algebra right here, but it's not the end of the puzzle. Right? These angles here are expressed in terms of alpha. We know they have to be equal, so, right, 25, alpha is 25, so 25 plus 75. This angle is 100 degrees, so is this angle is 100 degrees, because they're vertical angles, they're congruent. And this 4 times 25 is 100. So yeah, you can say this one is 75 bigger than 25, and this one is 4 times bigger than 25. So this is the answer, size of the angles. And you did this algebra to get this. That's 15B, page 44. All right. 15C on page 44. It says we have pairs of vertical angles from something like this. So we have this situation. We're going to use the most powerful word in mathematics, which is let. It starts with an L. So does the word label. So let's label these angles. These are vertical angles. They're congruent, so we'll give them the same symbol. These are vertical angles. And we'll give these the same symbols because these angles are congruent. And then we know if we add all of these up, alpha plus beta plus beta, we get 360 degrees. And it's given in the problem, 15C. See, the sum of the angle measures of one pair is 140 degrees greater than the sum of the angle measurements of the other pair. So sum of the other pair, obviously, is 2 alpha. And this sum right here says it's 140 degrees greater than this sum. So plus 2 alpha plus 140 equals 360. So here we have, 4 alpha equals 220. Alpha is 55 degrees. So that's just one of these. So one pair, and they don't give the names. They just talk about a pair of anonymous vertical angles. So we're giving it the names. But in the answer, it asks what are the measurements of those pairs. It's 55 degrees. That's alpha, and we know beta. These are supplementary angles because they're a linear pair. So we know beta has to be 125 degrees. That's 15C. 15C. Okay, here's 16. This will be the end of page 44. We are given this. MB, this line here, is parallel to PA. We're given that. We know that's true. And we're also given the fact that AM bisects this angle. And AN, this ray here, AN bisects this angle. So that means we have this and this are congruent. And we know that this and this are congruent. These are bisectors. We're given that. Given this stuff. Okay? We are to prove that MB is congruent to BN. Or measurement of that. I suppose we could just say, if we're using measurement, we're talking about number, length, we can use the equal symbol. We're to show that this is same length as this. That and that. So, How do we go about that? Well, let's see. We got parallel lines. The way they colored this in the book makes it easy to see this is a transversal, but these rays are also transversals. That means we know that this angle here is the same as this angle. And because this is also transversal, this angle here, we have alternate interior angles, same as that angle right there. So we have these triangles, these two trigons with two angles that are the same. That means they're isosceles triangles. And a theorem, let me check. Let me see. I don't know if it's listed in this book of the things we can use. It might be in the course book. You know, an isosceles triangle. Isosceles triangle. So these angles at the base, these are the equal angles. That means that this side in this triangle, this trigon here, these sides are equal. Well, this is also an isosceles triangle with these two angles at its base. And I'm talking about which triangle am I talking about? I'm talking about this triangle here. That triangle, this is also isosceles because these angles are equal. So that means these sides, this side is equal to this side. Well, there we go. MB, therefore, is equal to BN. So to prove this, in 16, what you do is you have to find alternate interior angles, identify isosceles trigons, and then what you know about an isosceles trigon, you match the sides with the base angles, and that's where you get MB, same size as B segment BN. And we'd say here that, well, we have this triangle MBA, and this shape here. Well, before we get to this trigon, we'll look at this trigon. Right, so trigon MBA is isosceles. I won't spell that whole thing, okay? I'll just put a period after the C. Triangle MBA is isosceles with MB congruent to AB. Here's MB congruent to AB. We also have trigon ABN. Trigon ABN is isosceles, and BN is congruent to AB. And if you remember, so we'll put these dots here. We'll say, therefore, we'll squeeze it right here. Therefore, that's what those three dots mean. A little stack of triangle dots. It's therefore. Therefore, MB is congruent to BN by the axiom transitivity of congruence. All right. MB is congruent to AB, and BN is congruent to AB. So therefore, MB and BN are congruent to each other. And that's the proof. That was number 16.